Hey everyone, and welcome. So if you're into ceramics, you probably spend a ton of time thinking about your clay, your slips, your glazes, right? But what about the stuff that makes all that work even possible? Today, we're going to go beyond the wheel and the kiln to really look at the hidden science of gypsum and cement. All right, let's kick things off with a big question. What really holds your work together? And I'm not just talking about the clay itself. I mean the molds you cast in, the patches on your kiln, the mortar that sets your beautiful tiles. Seriously, understanding these materials is a total game changer, so let's dive right in. These materials, gypsum and cement, they're the real unsung heroes of the ceramics world. From the plaster molds that let you make perfect slip-cast copies over and over, to the high-temp mortars keeping your kiln from falling apart, they are just foundational. But here's the thing. They are not the same, not by a long shot. To really get what makes them tick, we've got to look at how they harden up. And on a chemical level, we're talking about two completely different worlds.
Okay, so this slide right here, it really breaks down the core difference beautifully. With gypsum plaster, what you're seeing is a physical change. It's just simple rehydration. Think of it like reassembling a puzzle you've already solved. Cement, on the other hand, goes through this complex chemical reaction called hydration. It's like building a totally new structure from the ground up. Let's look a little closer.
Okay, so when you're mixing up plaster, what you've got in the bag is something called calcium sulfate hemihydrate. You just add water, and it physically reforms the exact same crystal structure it had as a mineral rock, becoming calcium sulfate dihydrate. It's really just a physical process. It's even reversible. It's all about recrystallization. Now, cement? That's a whole other ballgame. The moment you add water, you're starting this chain of irreversible chemical reactions. The compounds don't just recrystallize, they completely transform. They form brand new interlocking structures like calcium silicate hydrate, what we call CSH for short, and calcium aluminate hydrates, or CaH. It's these new phases that create this incredibly strong bonded matrix, and that's where cement gets its amazing strength. So in both of these processes, whether it's the physical thing happening with gypsum or the chemical thing with cement, there's one variable that you have total control over, and believe me, it is absolutely critical, and that's the water. I know it sounds basic, right? But you can't overstate this. The ratio of water to powder is everything. It literally dictates the final strength, the porosity, the durability, pretty much every single property you care about. And look at this graph of cement strength over time. It just smacks you in the face with the evidence. See those lines up top? Those are your low water ratios. They get super strong and they stay that way. Now just look down at the bottom lines. Those are the high water ratios. They don't start nearly as strong, and over time, they can actually lose a lot of their strength. The difference is just dramatic. Let's boil that down. Imagine the best possible strength you could get is 100%. Well, a properly mixed low-water cement might hit 95% of that. A high-water mix? You might only ever get to 30% of its potential. The difference is just staggering. So here's the golden rule, the main takeaway. Less water equals less porosity, which equals more strength. The less water you use, the tighter the particles pack together. This leaves less empty space, or porosity, in the final structure. And less porosity means, you guessed it, more strength. It's that direct. Okay, so now we get the how. It's all about that water ratio. But let's dig into the why. It all comes down to what's happening on a microscopic level. Because what's happening in the microstructure, well, that's destiny for your material. And this gets super important when you're dealing with some of these specialty cements, like calcium aluminates. Something really wild and honestly a little scary can happen. At first, they form these things called metastable hydrates, which gives them super high strength right off the bat. But then, over time, these can convert into more stable, denser crystals. The problem is, this conversion process actually squeezes water out, and that water creates new pores, which can weaken the whole structure. And don't just take my word for it, the research is crystal clear. This quote explains that this conversion process creates a porous structure that reduces the adhesion, and you get a notable drop in strength. I mean, that's a perfect example of how this tiny, microscopic stuff has a huge impact on real-world performance. So, does this mean porosity is always the enemy? Absolutely not. It's all about what you're trying to do. Think about a plaster slip casting mold. In that case, you want a certain amount of porosity. That's how the mold actually works. It sucks the water out of the clay slip to form your piece. But for a kiln repair, porosity is your worst enemy. It's a weak spot just waiting to fail under the stress of heating and cooling. All right, enough with the deep science for a second.
let's bring this all back to the studio and talk about choosing the right stuff for the right job.
So here's the deal. It's all about matching the material to the job at hand. For your everyday slip casting, a standard #1 pottery plaster is great because it has that controlled absorption. But let's say you're making a master model that has to be incredibly strong and dense. You'll want to step up to a gypsum cement like hydrostone. For setting tiles, you're looking at things like calcium aluminite cements, which get blended with gypsum to control how fast they set. And for repairing a kiln, only a heavy-duty refractory castable is going to handle that heat.
And, sometimes the real challenge isn't the project itself, it's the environment it's going to live in. Things like sulfates in the soil or acidic conditions can literally eat standard cements for lunch. That's where you need special engineered solutions. For instance, blending a cement with silica can help form more stable hydrates, creating these much more stable hydrates we call CaSH, and these are way more durable in those tough environments.
At the end of the day, what does this all boil down to? One word: control. When you understand the science that's actually happening inside that mixing bucket, you're not just following a recipe anymore. You're making smart choices. You're not just guessing anymore. You are empowered to control your process and get consistent, strong, and reliable results.
So I hope the next time you grab a bag of plaster or cement, you look at it a little differently. You'll know the why behind what you're mixing. So I'll leave you with this question. Now that you know, what will you build or cast or repair with a whole new level of confidence? Thanks for tuning in.